Introducing Naive Bayes Classifier. Have you ever wondered how your mail provider implements spam filtering, or how online news channels perform news text classification, or how companies perform sentimental analysis of their audience on social media? All of this and more is done through a machine learning algorithm called Naive Bayes Classifier. Welcome to Naive Bayes Tutorial. What's in it for you? We'll start with what is Naive Bayes, a basic overview of how it works. We'll get into Naive Bayes and machine learning, where it fits in with our other machine learning tools. Why do we need Naive Bayes? And understanding Naive Bayes classifier, a much more in-depth of how the math works in the background. Finally, we'll get into the advantages of the Naive Bayes classifier in the machine learning setup. And then we'll roll up our sleeves and do my favorite part. We'll actually do some Python coding and do some text classification using the Naive Bayes. What is Naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing two coins. Here we have two quarters, and if we look at all the different possibilities of what they can come up as, we get that they could come up as heads, they could come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting two heads equals 1/4. You can see on our data set we have two heads, and this occurs once out of the four possibilities. And then the probability of at least one tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting two heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with two coins it's easy to see, but when you have something more complex, you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case, the first coin toss will be B and the second coin toss A. This could be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our two quarters, and we'll notice that the first two probabilities of getting two heads and at least one tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4, or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with two coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also a reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the two heads and two tails and head, tail, tail, heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like. And then we're going to solve it in Python. And in here, we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Did we have a free delivery, yes or no? On those days, how many people made a purchase and how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays, there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities. And based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all three independent variables. Now we can construct the likelihood tables for all three of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these three likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We are actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B, B being all three categories, did we have a discount? with a purchase? Do we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data. So if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjusts for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the 2 overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walk through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes.